I'm at Red Hat, and I'm going to talk about Kubernetes running on OpenStack. So that is the server, OpenStack, and then containers on top. Okay, and I will also have two demos that I have pre-recorded. So I connected the audio here, so hopefully that'll all work and come through good. Okay, so what are organizations trying to achieve? Let me just, so I'm on till 2 o'clock, right? Okay, so, yeah. 2:05. Okay, we'll see how we do. Okay, so organizations are out to achieve agility, and there are several ways to achieve this. One of their attraction is public cloud, certainly. But for organizations that have already invested a lot in their internal data center, they don't necessarily want to chuck that out and go all in on public cloud and then maybe discover that the public cloud was wrong or too expensive or not the platform they were looking for. So they can take that internal investment that they have on-prem and leverage it to become more agile, to adopt cloud native, and to maybe stem some of the bleed to public cloud. Public cloud has its purpose, but it's not the be-all and end-all for everything. Okay, so there's the internal business. IT operations have those challenges to meet the challenges of internal business who want the speed, the agility that public cloud brings them, and developers want that platform of that API that they are familiar with. So, as many of us know probably by now, we're out to achieve digital transformation, cloud infrastructure, and modern application development. So developers want self-service, the business units want, the line of business also want the ability to self-serve. They want to meet the digital transformation that they feel they're being disrupted. This should be obvious to many people. Ride sharing disrupts taxis, food delivery disrupts restaurant businesses. So that whole digital transformation that I just saw, for example, news today that the bike sharing app that many people may have seen, these green and blue bikes. I just saw one right outside Intel here today. The blue one, there's a green one by a company called Lime. They just went into an agreement with Uber whereby you'll be able to find a bicycle using the Uber app with a whole bunch of money. So changes the way we get around, the way we transport, the way the world is changing very fast, and businesses have to adapt. Similarly, in a similar vein to this, I read a story yesterday that parking garages in Los Angeles, for those of you who've ever been to LA or lived there for any length of time, I pity you and the freeways, but I did my time in penance there. And there's a great cultural thing in LA, particularly I noticed, where when people go to restaurants, to nightclubs, to certain events, is you get parking. Often it's valet, you show up there, you give them the keys to your car, the car disappears, magically they find parking because no self-driving person there can ever find a parking space, but they find it. And many of these people run parking garages. Well, now with the advent of Uber, Lyft, and these other ride-sharing, parking garages are losing business enormously. And they have to find a way how they're going to transform themselves from a parking garage into, they have this empty lot, how can they transform themselves. So this whole idea of digital transformation is crossing many industries and boundaries. So IaaS, infrastructure as a service, is OpenStack and containers. So why do we want containers running on OpenStack? So IaaS, or infrastructure as a service, OpenStack, exposition of resources. What do they mean? You mean you have a bunch of servers there, you have storage, you have networking, and OpenStack exposes the compute, the storage, and the networking up and creates pools of that, which can then be consumed, in this case, by containers. So we can move apps, and we want automation at both layers. So when a new server comes online, OpenStack can automatically grab it, add it to its pool of resources. When the server goes away, it can reduce that pool. So that whole automation of spinning up, creating new compute storage and networking by OpenStack, and then similarly automate containers on top of that to consume that. So the old way was buy a computer, plug it in, connect the network, and SSH. Rinse, repeat. How do you scale this? How do you take this old manual process and do that in a very much repeated fashion, automatically recognize new servers that they come online? OpenStack has this project called Ironic, which is bare metal provisioning. You can take that server, add it into the pool, and it automatically expands the pool of compute networking and storage. This sort of old manual process doesn't need to happen. So again, we changed the way it was inefficient. So just like exposing resources, consuming them has changed as well. There's a tree of processes that are running. Now you can separate those processes into containers. Each container runs its own process. If it dies or it needs to be replaced, you don't have to yum update the entire server. You just update that one container running that one very small microservice and continue running that way. So it's a changed paradigm of doing business. So again, these containers provide something called standardization for performance and capabilities. So we load, where they say here, load applications at the factory, not at the dock. So you don't, you load your apps when they're needed, when the server rolls out. Later on go the apps. They are automatically provisioned, automatically updated. If there's a virus, if there's a small part of the app that needs to be updated, go ahead and only update those few containers, those few binaries, and not the entire server. And you can move that container between environments. You can move it between a public cloud, between a private cloud. Depending on how your orchestration is set up, you can maybe move it across different public clouds onto OpenStack. So that whole idea of portability, because you have a standard environment by which it's created. So how does Kubernetes and OpenStack help you achieve this? So again, the infrastructure as a layer, as I said, is exposed. So OpenStack at the bottom will expose the processes, the distributed systems, and at the top, Kubernetes will consume it. So you'll see there's a later diagram coming showing how this matches it a bit better. But processes call system calls, containers perform system calls, distributed systems perform APIs, and Kubernetes will go onto OpenStack and say, give me some storage, give me some networking, give me some compute, and that will be provided by OpenStack. So again, it does that, the idea of rinse and repeat automation. So there are a number of ways of automating things in OpenStack. We have one popular one, there's Chef, there's Puppet. Another popular one is Ansible, which provides playbooks where, again, you can do a lot of this automation. You run them at the command line. Playbooks are very reusable. There's an upstream repository of playbooks where you can contribute your code into them, you can download them. So it provides a way to do a lot of that automation. And again, so Kubernetes are grouped into what's known as clusters, and there are groups of, again, containers. They're orchestrated, and there's a self-service portal by which you can come into the request for a container, for several containers. You can create what's called a pod. You can group them together and then define and share your applications into that and consume them with OpenStack. So we put all together. We have OpenStack underneath, we have Kubernetes, and then you have the application on top. So this is what Kubernetes and OpenStack will look like. You have your standard hardware. OpenStack, again, has shared compute, networking, and storage, okay, which has consumed from the hardware beneath that. KVM would be the hypervisor. which is the hypervisor of choice in most open source environments today. If you wanted to run on bare metal, there's a project called Ironic, and that means you can run your containers directly on the hardware without having the virtualization layer in between. That can be preferable for maybe certain high-performance type applications. There's two hardware companies I know right here in this valley that are doing this on bare metal, where they have certain performance tests of their chips and their semiconductors. They're using our products, and they rapidly provision and deprovision racks and racks of servers using Ironic, using the OpenStack project and Ironic to provision them, perform the tests, deprovision them, return them back to the pool. Okay? If you're running virtual machines, then you have a virtual machine sitting on top of KVM, or you have your container sitting on top of the virtual machine, or the container sitting directly on the server on the right here, where you see the container sitting on the Ironic and the bare metal. So here we have some of the advantages, okay? So again, this is all API driven. This is not necessarily GUI click like some other companies do, where they admins and users in those environments are very accustomed to more of a GUI click type environment. This is not. This is API software driven. Much of it is command line. There are Ansible and other types of playbooks that you run at the command line. You can certainly run them through a GUI, but it's often command line driven. And it's fully automated for Kubernetes to consume OpenStack. You have a consistent infrastructure experience, okay? And you can provide isolation for each workload. So some workloads, again, if you go back to this diagram here, you can isolate them onto maybe bare metal. You can isolate some onto this virtual machine or other virtual machines, but you can achieve a sense of isolation. In some environments, for example, in the telco environment, there's something called, and others, there's something called multi-tenancy, where you have many tenants. Multi-tenancy, think of an apartment building or a multi-use office building. So there are tenants there, and tenants rent out office space in that building, or tenants rent out apartments in a apartment building. And what does multi-tenancy mean? You're all sharing some kind of infrastructure, but you have a sense of isolation. So me in my apartment in that building, I'm isolated, I have my privacy, I can live there as I wish, obviously within certain rules, but I share the infrastructure of the parking garage, the roof, maybe the common area at the back, the elevator, the stairs. So I share that infrastructure, but I am a tenant in my own right, and I will get billed for my usage of electricity, water, power within the building. I'll get a sub-billing of the common, I'll have to pay for a share of the elevator, stairs, backyard, roofing, painting, etc. that has to be done. So that's what we mean by multi-tenancy. So they can be isolated. So I'm isolated in my apartment or in my own office. I'm firewalled, I'm protected, I don't necessarily have noisy neighbor interference. Unless obviously there's a leak from the upstairs neighbor or a noise from the one next door, but generally you have a sense of isolation, but I'm sharing that infrastructure. So the same idea here is you have the shared infrastructure at the bottom, and then you can have applications and containers running in isolation on top. And greater density over bare metal. So on the right here in the Ironic, we have running on bare metal, you may have a smaller number of containers because they are all consuming that quad-core CPU, all those CPUs or all that memory, all that storage dedicated by that one server. On the left two columns, you have more of a shared infrastructure. So the servers that are dedicated to the KVM and the virtualization layer are more shared, and you get more density. So you get more density on the left, but it's shared. So you may have a slightly performance hit. So the choice will be, do you want higher performance on a dedicated server using Ironic, or do you want more density using less servers but maybe taking a smaller performance hit on the left? So those were some technical advantages, some of the business advantages, okay? Again, apps design the platform suited to their needs. So if you need bare metal, you get bare metal. If you need shared, you get shared. Reduce the time, again, we'll be talking about automation. Developers to focus on application functionality and features, so they don't need to worry about. The advantage of this kind of thing is developers don't need to go and provision storage, networking, and compute for themselves. That is provisioned, they just need to consume it. Okay? It's more efficient and you can scale. So, OpenStack and Kubernetes, as presented by Red Hat, is the Red Hat OpenStack platform and Red Hat OpenShift. So, Red Hat OpenStack platform is our distribution of the upstream OpenStack. It is a 100% open source. There is no secret source in there. There's none of the code inside any of these two products is private. It's all in the upstream. So everything that Red Hat does is done in the upstream. So the Rocky release, the Queens, going back to Grizzly, each of the releases has code in the upstream. The code in the downstream Red Hat product is the same. There is no fork. There's no concept of private extensions. So OpenStack will be the shared services here in red at the bottom, and the Kubernetes layer at the top will be what we call OpenShift. So how do the two sort of map together since they're on top? So the idea of Keystone is the project in OpenStack that does identity or logins. Ceilometer is the metering project in OpenStack. Horizon is the dashboard. And at the top there you see, so the dashboard is your sort of portal environment, and that allows you to provide multi-tenancy. So each tenant will take that dashboard and get their own view of the resources provided to them. The Heat project in OpenStack provides orchestration. The Nova project in OpenStack provides compute. Neutron provides networking. Cinder provides persistent storage. Load balancing as a service provides load balancing. Designate provides DNS. And Ironic is their provisioning of hardware into the pool of available resources. So let's take a deeper dive into storage. I'll do one on storage and one on networking. So OpenStack again provides a project called Cinder for persistent storage and virtual machines. And then OpenShift is sitting on top with those applications running on those virtual machines. And the application will say, I need a persistent volume. What does a persistent volume mean? It means that when that Kubernetes application ceases, the data will continue to live. Okay, many times applications are deployed, if they're what's known as ephemeral, it goes away. As soon as that container is destroyed, which happens very frequently because containers are fast-living environments, then the data that the container stored was destroyed. But we may need it to persist, to remain longer, so OpenStack can provide that. And let's have a demo of that.
To really understand the value of OpenShift running on OpenStack, it's important to take a look at a traditional IT environment. So in a traditional environment, if you install OpenShift,
Hang on.
Maybe just put your microphone near it.
You'll give the developer access to self-service, to applications and storage and network, etc. To really understand the value of OpenShift running on OpenStack, it's important to take a look.
I'll just.
It's only going to their speakers.
To really understand the value of OpenShift running on OpenStack, it's important to take a look at a traditional IT environment. So in a traditional environment, if you install OpenShift, you'll give the developer access to self-service, to applications and storage and network, etc. But when they try to provision an application that needs storage, OpenShift will create what's called a volume claim, and this volume claim is satisfied by what we call a persistent volume. These persistent volumes then have to be attached to actual real storage in some way, shape, or form. In a traditional environment, you could wire it up so that a persistent volume, every time one is created, it goes and fires off a ticket. A storage administrator, eventually gets a hold of that ticket, works through the ticket, provisions a storage, and then hands it back to OpenShift. But that would be a slow manual process. In an OpenStack environment, if you run OpenShift on OpenStack, OpenStack happens to be really good at automating this exact kind of operation. So ahead of time, the storage administrator would come in and set storage policy and quotas, but then these volumes could be provisioned automatically, and they could be provisioned based on policy as opposed to a manual intervention every time. Now we're going to do a quick demo to show how powerful the integration between OpenShift and OpenStack is. On the right, we have a persistent volume claim set up ahead of time. We're going to submit this persistent volume claim to the OpenShift API to provision it.
Did you go to full screen?
You'll notice on the left now, a persistent volume has been created to satisfy the persistent volume claim, and immediately following that, OpenShift talked to OpenStack, and in the bottom left window, you saw that an OpenStack Cinder volume was created to satisfy this persistent volume with the exact size needed. And when you think about doing this at scale, that's when this becomes really powerful. So not just a single application, but when you start to look at running many applications together in a multi-tenant environment, this becomes very, very powerful. You can imagine with tens or hundreds or thousands of applications, you could not scale, with a manual intervention process where a storage administrator comes in and provisions a storage. So that's where OpenShift on OpenStack really shines.
Okay. So networking. Okay. So now we'll discuss networking, and I'll play another demo. Okay. So OpenShift and OpenStack lands up with what's called encapsulation, or you can have two networking layers, and this needs to be solved. One networking provided by OpenStack and the other networking provided by Kubernetes or OpenShift. So there's a project called Courier, which allows the same simplified networking. So it eliminates the need for multiple network overlays when using OpenStack on OpenShift. Gives you better performance, higher bandwidth workloads, and eliminates that double encapsulation problem. This means that you can have virtual machines and containers on the same network. Again, it's an open source project, 100% open source. Red Hat we just released it in our latest Queen's release of OpenStack. And how does it do that? So it's called a CNI plugin, container native plugin, and a controller to integrate Neutron and Kubernetes. So here you see the virtual machine from OpenStack and the container both using the same network.
In this video, we're going to be demonstrating the upcoming Courier integration between OpenShift and OpenStack, and looking at what we can currently do today. On screen, you can see the most basic premise of Courier, allowing OpenStack provisioned instances to communicate with OpenShift provisioned pods or containers on the same Neutron network. Now, it's important to point out that it is generally understood that for Courier to work, the OpenShift nodes need to be running on top of OpenStack-based virtual machines. But actually, much of the work in Courier is to allow the same network extension to exist for bare metal machines provisioned through Ironic 2, although we're not going to be showing that in this video. So let's get started with an environment based on DevStack. First, we'll look at the current list of OpenStack networks. And the most important network for us to be concerned with here is called Kubernetes PodNet. What you don't see here is that Courier, as a container network interface, or CNI, is configured to use this network for all new pods launched from within Kubernetes. But forget that for now. We'll come back to it later. First, we're going to grab the network UUID for this network, as the aim is to launch a standard OpenStack instance or virtual machine on this Neutron managed network. We'll just create a really basic virtual machine based on Cirrus, but we'll specify the pod net as the network we want OpenStack to put it on. Okay, so after a few seconds, we should see that this machine has come up and has been given an IP address on our Kubernetes pod net, 10.0.0.74 to be specific. Ignore the AM4 or VMs for now, we'll explain those later. As this is a standard VXLAN-based tenant network, I can't route to that network without you going through the network namespace. Here we can see that the VM is alive and kicking on that assigned IP. Let's make that slightly easier for ourselves by assigning a floating IP to this instance. You'll have to forgive me for using some of the older command line tools here, it's just force of habit. Now that we've got the port ID, let's generate a floating IP on the public network, one that's routable from the machine shown here in the video, and we'll assign that directly to the port. Now I can secure shell directly to that machine on the public network, noting that when I'm in, the only IP address we've got here is the internal tenant network address, just like it would be in any normal OpenStack configuration. Up to this point, I haven't really done anything magical. All of this is completely standard OpenStack stuff and has absolutely nothing to do with Courier or OpenShift. We're just setting it up for the rest of the demo and to prove that Courier is functional between OpenShift and OpenStack. Let's now dive into the OpenShift side of things. As you can see, I have no pods currently running. Let's ask OpenShift to run a demo application. The one that I've chosen is an application that currently resides inside of the Courier repo and is a really basic HTTP server that announces who it is over port 8080 and has helped with some of the Courier development. It's also really lightweight, so it's perfect for basic functionality testing. And yes, I know I should have used OpenShift tooling here instead of kubectl, but again, that's force of habit too. As you can see, it's created a new deployment for us, and we can watch to see it create pods and the associated containers for us. After a few seconds, you'll notice that our container is running and has been assigned an IP address in the same range as the Kubernetes podnet as defined in Neutron, this time IP 10.0.0.70. If this was really a Neutron network, I should be able to ping the IP address just the same as I did the OpenStack instance, right? Well, let's try. There we go, so good so far. As I've commented on the demo, this pod should announce a hello world or a hello I'm alive if it's contacted on port 8080. But rather than trying from the namespace like we just did with the ping, let's make this a little bit more interesting and see if we can contact that IP address from the OpenStack instance itself. First, let's jump to that virtual machine on its floating IP. Now that we're here, let's curl the pod's IP on port 8080. There we go. So we've proven that an OpenStack instance can communicate with an OpenShift container on the same Neutron-based overlay tenant network. But the integration between OpenStack and OpenShift with Courier doesn't end there. The whole idea of making OpenStack the best place to run OpenShift is based around the integration of many different areas and the reuse or the leveraging of existing functionality. We've shown basic network integration so far, but one of the key areas that Courier engineering teams have been working on is with the load balancer as a service integration. When you run OpenShift on top of any of the public cloud platforms, they all have specific mechanisms to expose a pod on their platform, so it can be routed from the outside and can optionally be load balanced for distribution of service and also resiliency. With OpenStack, the engineers wanted it to be the same, and Neutron already has a load balancer as a service functionality built in. The first thing we need to do is tell OpenShift to expose the deployment that we've got running, making it clear that we want to expose this on the standard HTTP port, i.e. 80, but the target or actual port our containers are listening on being 8080. This creates a Kubernetes service and also sets a cluster routable IP address to access this service on. In our case, this comes out as 10.0.0.150, again, right on our Neutron network. The integration here is key. The service is configured to dynamically provision an OpenStack-based load balancer through Octavia, our implementation of Neutron's LBAS v2 functionality. As Octavia provisions a whole new virtual machine based on AM4 to host HA proxy instances, this can unfortunately take some time. So we're going to zoom through this part, but we'll constantly watch the output change every 5 seconds. You'll note that the state starts off as pending create. It's also been given an IP address of 10.0.0.150, which you'll recognize is the exact same IP address that is the cluster routable virtual IP address from Kubernetes. After a few minutes, this will move into the active state. When we look at the output of the service info for Kubernetes, you'll notice that it is created with a selector. This selector is chosen dynamically when we invoke the expose command rather than creating the service manually. This ensures that the service knows which pods are exposing an endpoint for the load balancer, here based on the demo name. Right now, this service is only routable from within the cluster. It may be based around an OpenStack provisioned load balancer, but it's only been created with an internally facing virtual IP address. It is possible to have Kubernetes via Courier and the existing OpenStack integration to dynamically associate a floating IP, but I'm going to complete this manually just like we did for the OpenStack VM. If we grab the port UUID for our load balancer on the internal network, we can request a new floating IP from the public network and have it bind directly to that port using the standard Neutron L3 functionality. Here we've been assigned 172.24.4.11. If routing is working, we should be able to curl this IP address straight away, recalling that we set the service to listen on port 80, but route back to port 8080 on our containers. Hence why we're not specifying a specific port here. And there we have it. The pod is routable from the OpenStack-based external network, going through Neutron's L3 service, into an Octavia-based load balancer, and connecting to an OpenShift-based pod on the same internal network, all of which has been plugged by Courier. We can ask OpenShift for the list of current endpoints for the demo service, and you see that it's only showing the one pod that we created earlier, and that the IP address for the endpoint matches the IP of the pod itself. But this isn't exactly demonstrating load balancing here, it's just one endpoint it has to connect to. So let's scale our deployment out to 5 separate pods using the OpenShift command line tooling, setting the replica count to be 5. We can then monitor the pods as they're being created. It takes a few seconds to get all of them up and running, but eventually they'll all come up. Noting that they've all been assigned a different IP address within the Kubernetes podnet. Because we scaled the deployment, the service should automatically get updated with all of the new and available endpoints it needs to load balance across. So when we hit our load balance public IP again, it should start to load balance across all of our available pods. Note that on the second attempt that we tried then, it showed a different UUID, and it will continue to do this over round robin by default. There we go, that's the end of the demo. At this point, it's worth mentioning a few things. The longer-term strategy is to remove the reliance on Octavia and implement OVN's distributed load balancer functionality, as starting virtual machines to implement load balancers with OpenStack simply takes too long. And from an OpenShift perspective, it becomes frustrating for operators waiting for that to actually start working. Also, Courier only currently supports Open vSwitch-based implementations such as ML2 OVS or ML2 OVN, as it relies heavily on Neutron's trunk port functionality, which many of you may know more commonly as VLAN-aware VMs. And not all third-party plugins can do this right now. Finally, as I highlighted earlier, it is possible to integrate bare metal nodes or bare metal OpenShift nodes with Courier. And there's a great demo available on YouTube from DevConf. If you're interested in seeing this in action, please go and look it up. Thanks for watching.
Thank you. So in closing, OpenShift and OpenStack are just a portion of the entire cloud suite that we offer. OpenStack is here. There's OpenShift, as I say, containers, but it's managed with a product called CloudForms and Insights for operations. There's a virtualization suite and a management suite as well, and storage and running on RHEL Linux. So that is it. There are 2 minutes left.